Today we are going to be talking about the chemistry of water and how important water is to living cells and to the evolution of life. So just the objectives. So water is the biological medium on the earth. All living organisms require water more than any other substance. And so water is actually considered an essential nutrient, right? So water is a nutrient and all forms of life need it. Most cells are surrounded by water, and of course the cells are full of water, right? 70 to 95% is water inside a cell. And the abundance of water is the main reason why the earth is habitable. So when it comes to planets orbiting suns, there is a region called the zone of habitability where they're not too close, not too far away, right? It's the Goldilocks zone. It's just right. But all this water that's on the earth actually helps us to be just outside of the zone of habitability because we have so much water. And that water helps to maintain a relatively stable environment on the earth. It may not seem like it to us, right? Because it gets really hot in the summertime and can get really cold in the wintertime, but that's actually a narrow range of temperatures. And life can exist at those narrow ranges. So again, right, the big blue marble in the universe, right, because we have so much water on the Earth's surface. And you may think, well, it's salt water, right? It's seawater. Yeah, we can't drink it, but seawater is actually a rich environment for all kinds of life. We already learned that water is a polar molecule, right? That big, strong oxygen atom is much more electronegative than those hydrogens. And so the electrons are pulled closer towards the oxygen. And that gives the oxygen a partial negative charge. And the hydrogens have partial positive charges. And we said that that allows for hydrogen bonds to form. And those hydrogen bonds are extremely important when it comes to the stability of water. And so those polar covalent bonds between the oxygens and the hydrogens allow for those partial charges and allow for the formation of hydrogen bonds. So water forms many hydrogen bonds with itself. So even though water is a liquid, and water is not strong, right? You can put your hand through it, you can swim through it, you can do all kinds of things with water. The hydrogen bonds are constantly being formed and constantly being broken, right? Because water molecules are constantly in motion. All molecules are always in motion. Some are just faster than others. Even the, tabletop or your laptop, it feels hard and solid, but the molecules are actually moving just very slowly. So water has 4 important properties, and that helps to create a favorable environment for life to exist. Water is cohesive. That means it sticks to itself. It has the ability to moderate temperature, as we're going to see. It takes a significant amount of energy to raise the temperature of water, and it also takes time for that water to cool down. And that makes water more stable. Water expands upon freezing. So water is one of the few liquids that actually expands. Almost everything else will contract. When they freeze, right, they shrink. And water is considered a universal solvent. So water will and can dissolve away solid rock. It takes millions of years, but give water enough time, it'll dissolve away anything. Look at the Grand Canyon, right? Water has slowly eroded away, the canyon, right, to make it the Grand Canyon that it is today. So hydrogen bonds hold water molecules together, and we call that cohesion. So like I said, the water is sticky. And we don't think of water as sticky, but it is. If you wash and wax your car, and then it rains, the water stands up. It beads up, right? It doesn't spread out and form a thin layer across the surface. It beads, it stands up. And we've all probably seen this, or maybe you spilled some water on the table or something. And so you see that the water, it stands up. It doesn't spread out. It stands up because the water molecules are sticking together. And that's because of those hydrogen bonds. If you take something like alcohol, alcohol does spread out because there's nowhere near as many hydrogen bonds in alcohol as there is in water. Now, cohesion helps plants. So plants have to absorb water through the roots, and the water has to travel up through the stem and then out the leaves where it evaporates. Plants don't have hearts, they don't have a pump, right? There's no way to force the water up through the plant. It all happens because water is sticky. It moves into the little tubes, which are called xylem in plants. And so what happens is, as the water molecules move in, they grab onto the sides of those xylem tubes. We call that adhesion. And then as the water grabs onto the sides of the tubes, cohesion pulls more water molecules up, right? So the water molecules are sticking to themselves. They grab onto the sides of the xylem, and then they pull more water molecules up, and then they grab higher up and pull more water molecules up. And so water actually just automatically travels up through little skinny tubes. We have those same kinds of things that used to be used in hospitals and doctor's office when they took a little blood sample. I don't know if they still use them or not, but they were little thin glass tubes, real tiny, like about the size of a toothpick, but they were hollow tubes. And so they prick your finger, right, to get a drop of blood, and they put the tube over the blood or into the drop of blood, and the blood just moves right up the tube. If you did it with a drop of water, right, the water would move right up the tube. So we call that capillary action. So that just happens because water is both cohesive, it sticks to itself, and it's adhesive, it sticks to other things. And that's all because of the hydrogen bonds. So because water has all these hydrogen bonds, plants can easily absorb water and move it up through the plant where it evaporates out the leaves, and that keeps the water flowing. But that's a property of hydrogen bonding. So, right, it's, the xylem forms the little tubes. And so xylem, the water moves up through the roots, right, and through the stems and out the leaves. And it all happens because water is sticky. It can stick to the sides of the xylem tubes, and it sticks to itself, or it sticks to other water molecules. So adhesion means the water sticking to something else, and cohesion means the water molecules are sticking to themselves. But that's all because of water. Other liquids do not do this. Surface tension is a measure of how hard it is to break the surface of a liquid. So again, we think, because we can easily stand in water, we can jump into the water, and we, go right through the water. So we think, well, water doesn't really have much surface tension, but it actually does. If you're light enough, you can actually walk on water. So if you've ever been to a pond or a calm river, you may have seen these insects called water striders or water skippers. And here is one of them. And you see, it does not break through the water. It actually walks on water because water has surface tension because of those hydrogen bonds. It takes a certain amount of effort, not much, but it takes some effort in order to break through the surface of the water. And so if you're a light insect, you're able to spread out your legs, you can actually walk on water without breaking through and falling, sinking down into the water. And that's because of all the hydrogen bonds creating that surface tension. So water absorbs heat from warmer air and releases stored heat to cooler air. So water can absorb and release a fairly large amount of heat with only a slight change in its own temperature. So that's an important point. Water can absorb heat energy and it can dissipate heat energy, but it doesn't change the actual temperature of the water that much. And that makes water very stable because life needs a stable environment. So we mentioned energy last time, and we'll go into much more detail about energy in a future lecture. But kinetic energy is the energy of motion. So molecules are always in motion. They're always moving. Some molecules move more quickly than others, but they're always moving. Adding heat increases the kinetic energy of molecules. So when you increase temperature, molecules move faster. If you boil water, the water evaporates because the molecules are moving so fast they change state from liquid to gas, and so they evaporate. So heat can be used to measure the total amount of kinetic energy due to molecular motion. But by increasing the temperature, right, by adding more heat, you increase kinetic energy. And temperature is simply what we use to measure, right, the heat. And that's due to the average kinetic energy of molecules. So we've all measured temperature. We know about air temperature. Or when you're cooking, you may try to cook your food to a certain temperature to make sure it's done. We already talked about how, because it's science, we use the metric system, so we use the Celsius scale, right, to measure temperature. And many of you are familiar with Celsius. At what temperature does water boil in Celsius?
100 degrees.
Right, so 100. And the freezing point?
0.
Is 0. So for those Americans who only know Fahrenheit, in the Fahrenheit scale, a boiling point is 212 degrees Fahrenheit to boil, and 32 degrees Fahrenheit for freezing. And that's why I said the other day that if you say, oh man, it's so hot, it's going to be 35 degrees, that just doesn't sound right to Americans. They just can't deal with that because 32 is freezing, for them. A calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. So that is the definition of a calorie. It's the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. Now, when it comes to dietetic calories, they're not the same thing. A dietetic calorie is actually a kilocalorie. It's actually 1,000 calories. And so if you eat a candy bar, right, that's 300 calories, it's actually 300,000 calories that you're eating. So, dietetic calories are actually kilocalories. When they say the average person needs 2,000 calories a day, what they're saying is you need 200,000 calories a day. So it's a lot. A joule is another unit of energy where 1 joule is equal to 0.239 calories, or 1 calorie is 4.14 joules. You don't need to remember that, but if you go on to take chemistry and physics, you're going to use the term joule, for energy. So you will see that again. Oh, when I said 2,000 calories, I meant you're actually eating 2 million calories, right? 2,000 or 2 million calories, not 200 calories like I said before. The specific heat of a substance is the amount of heat that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degree Celsius. So these are standard definitions that they use, to talk about, the different specific heats of different substances, or heat capacity, which I'll mention in a moment. So these are specific definitions, for these things. And so water, by definition, has a specific heat of 1 calorie per gram per degree Celsius. So we use water as the standard, and then all the other specific heats for every other substance are relative to this definition of water as having a specific heat of 1 calorie per gram per degree Celsius. Water resists changing its temperature because it has a high specific heat. So the reason why it has a high specific heat has to do with all the hydrogen bonds. When heat gets absorbed by water, hydrogen bonds break because the water molecules are moving faster. When water cools down, it releases heat, and so the molecules slow down and they form hydrogen bonds. So again, it all has to do with the hydrogen bonding. The high specific heat of water minimizes temperature fluctuations. So again, life, any particular organism can only exist within a relatively narrow range of temperature. Now, life forms can exist at different temperatures. There are microorganisms whose ideal environment is 100 degrees Celsius. So they grow in boiling water. They thrive in boiling water. But that's not for us or for complex multicellular life forms, right? We can't handle that. That's too extreme for us. But there are different forms of life that normally live at different temperatures. When it comes to freezing cold, you can have liquid water at 0 degrees Celsius. How can you keep water from freezing at 0 degrees Celsius if that's the freezing point? How can you have liquid water at 0 degrees Celsius? Right, so other molecules, other solutes, like salts, even proteins, right, can actually lower the freezing point. So as long as water is liquid, life can exist in it. So it could be at 0 degrees Celsius, and there are forms of life that's their ideal temperature, is 0 or near 0, right, as long as the water stays liquid. At the other extreme, as I mentioned, we have forms of life, microscopic forms typically, which can grow around the boiling point of water. So that is what they need to thrive. Obviously, if you take something that likes, boiling temperatures and you cool it down, it's not going to grow, right? And eventually they'll die because they like the heat. And if you take something that loves the cold and you warm it up, you're going to kill it, right? So any given organism can only survive within a relatively narrow range of temperature. Now, humans, we're special, right? Because we're smart, or at least we think we're smart. So, like I said last time, or on the first day, we can change our environment to suit us, right? We wear clothes to stay warm. We make heat in our homes so we can stay warm in the wintertime. We have air conditioning in the summertime so we can stay cool. So even if the outside temperature is not really ideal for us to survive, we have created ways, to get around that so we can survive. Nothing else can really do that like we can. So here we just see some examples, right, to show you that water is the most stable substance because it takes a relatively large amount of energy to increase the temperature, and it also takes time for water to cool down, so that makes it more stable. So here we're looking at heat capacity, which is the ratio of heat absorbed relative to the temperature change of that material. We notice here water has a high heat capacity. Compared to everything else here, it takes a lot more energy to heat up that water, right, than it does to heat up any of these other substances. And so the point is, water is stable. It creates a stable environment for life to exist because water does not heat up too quickly. It does not cool down too quickly. So it maintains stability in that stable environment. We talk about the oceans and global warming. If the ocean temperature rises by a few degrees Celsius, that can have a dramatic impact on the things that live in the ocean. And it can kill some of those things because that's too drastic a change, right? Because oceans are huge. It takes a lot of energy to heat up those oceans. It also takes a lot of time for the oceans to cool down. So global warming is causing the oceans to heat up too much, and that is causing stress to the life forms that live in the ocean. And when we talk about human beings, if somebody said, well, yeah, the average global temperature, it might increase by 3 degrees Celsius, and you're like, well, 3 degrees, that's no big deal. So instead of it being 93 degrees, it's 96. It's still hot, but hey, that's not how that works. The average temperature increase will be 3 degrees. It's not going to be 3 degrees everywhere. It's going to fluctuate wildly, and it causes or will cause dramatic effects to weather. Warmer oceans cause more hurricanes, and they're more severe. So, there are impacts to global warming, and people, you tell them, it's like, oh, well, the temperature might increase by 3 degrees, and you're like, oh, 3 degrees, so what, that's no big deal. It's huge because water is stable, right? The earth is stable because of all the water. If you're increasing the average temperature by 3 degrees, you're inputting a lot of heat energy into the oceans, into the planet. And that's going to have dramatic effects in all different parts of the world. So what may sound like a small increase is actually huge in terms of the effects it will cause, because water maintains this stable environment. So we know that when water evaporates, it takes heat energy with it. So that means it cools. So the heat of vaporization is the heat a liquid must absorb for 1 gram to be converted to gas. So I've told you that by boiling water, you can convert it from liquid state into a gaseous state because the molecules are moving so fast they actually evaporate right into the atmosphere. But as that water evaporates, it cools. And so evaporative cooling is something that organisms like us humans use, right, to help cool down. You sweat. When that sweat evaporates, it takes heat energy with it, and that helps cool you down. Evaporative cooling is most effective when the humidity is low. If the humidity is high, like what we get here in this part of the country in the summertime, you can sweat all you want. It doesn't evaporate because there's so much moisture in the air. It's harder for the sweat to evaporate. So when they talk about you know, a dry heat. They joke about, oh, how hot is it? You know, it's so hot, but yeah, it's a dry heat. It does make a difference. In a dry heat, the humidity is low, which means when you sweat, it evaporates and you cool down. But when the humidity is high, right, the sweat doesn't evaporate, so it's much harder to cool down. When I talked about the evaporation of water from the leaves of plants, in a dry climate, plants would tend to lose a lot more water, right, through evaporation, as opposed to a humid climate. So all these factors will affect life. When a body of water needs to cool down, some water will evaporate. You've seen this if conditions are right. Have you ever seen fog on top of a lake or maybe on a river? It's because the river was warmer than the air temperature, and the water evaporates and then condenses in the cooler air temperature, and you get a fog. But that helps to cool down bodies of water. Now, when it comes to ice floats in liquid water because ice is less dense than water. And the reason why is as those water molecules start slowing down because they're cooling down, so their molecular motion is slowing down, then the hydrogen bonds really start to have an impact. And all those partial charges, positive charges on the hydrogens, negative charges on the oxygens, we know that opposite charges attract, but like charges repel. And so you have this battle between the like charges and the opposite charges, and that causes the water molecules to become very ordered. So they basically have to spread themselves out. So those partially negatively charged oxygens don't get too close together, and the partially positively charged hydrogens don't get too close together, right? Because like charges will repel each other. And that's why water expands when it freezes, because it's trying to minimize like charges coming close together and maximize the opposite charges coming close together. And so water molecules actually form a lattice structure. And so water expands, and therefore it's less dense. Water reaches its greatest density at about 4 degrees Celsius. So 4 degrees above freezing. So the water is really cold, and the molecules are slowing down. But as soon as they get even colder, they'll start to spread out, and the ice becomes less dense. Now, ice over bodies of water has a benefit. Ice over bodies of water helps to insulate the ice. And so if ice sank, then the water on top would freeze, and then that ice would sink, and then the water would freeze, and the ice would sink, and eventually the whole body of water would be frozen solid, and then life could not exist. So ice is less dense, it floats, it forms an insulation, a layer of insulation on top of that body of water, which keeps the rest of the water from freezing. And so life can exist under those bodies of water. When it comes to small lakes and ponds and things, most of the time, all the water does not freeze solid, and that allows for fish and frogs and things to be down at the very bottom in the liquid water so they can survive the winter until the ice melts. If the whole thing were to freeze solid, it would kill, the fish and the frogs. When it comes to the oceans, the oceans are really deep, right? So you have an insulating layer on top at the polar regions, but there's tons of life under the ice, right? Because the water is still liquid. It's very, very cold, but it's still liquid. So ice is less dense because the water molecules become very ordered and form a lattice structure. So they kind of spread out, and that makes ice less dense, so it floats. And floating ice insulates the water underneath to keep it from freezing. Because if the ice sank, all the water would freeze, and the Earth would just be a frozen ball in space. No life. And here we see those water molecules. Notice how in ice, all the water molecules are spaced out. In liquid water, they're closer together because, they're moving around, right? They make and break hydrogen bonds, so they're constantly moving. But liquid water is more dense than ice, and so your ice floats. So that, again, is an important property of those hydrogen bonds, and that helps to make water a stable environment for life to exist. Any questions about anything? Feel free to interrupt and ask if you have a question. So we make a lot of solutions. So a solution is a liquid that is homogeneous or is a homogeneous mixture of substances. The solvent is the dissolving agent, and for our purposes, it's almost always water. And the solute is that which is dissolved in the solvent. So salt water, water is the solvent, salt is the solute. In a sucrose solution, water is the solvent and sucrose is the solute. So an aqueous solution is one where the water is the solvent. So in biology, almost every solution we use is an aqueous solution. It's a watery solution. So we talked about how water is a universal solvent. That has to do with its polarity, allows it to form hydrogen bonds, so it can help to dissolve many other substances. When it comes to ionic compounds like sodium chloride, which is dissolved in water, and you have those positively charged sodium ions and then negatively charged chloride ions, they actually get surrounded by water molecules. And we call that a hydration shell. So, right, the partial negative charges on the oxygens are attracted to the positive sodium, and the partial positive charges on the hydrogens are attracted to the negative chloride ion. And so in an ionic solution, you have this hydration shell where the ions are surrounded by the water molecules. And that helps those compounds to dissolve in water. Water can also dissolve compounds that are not ionic polar molecules. Large polar molecules like proteins, they can dissolve in water if they have ionic and polar regions. So remember, a protein can be very large. When we learn about the amino acids, we'll learn that some of them have charges associated with the amino acids. So you can have regions of a protein that have partial charges on them. And so a hydration shell can form around those proteins so they can actually dissolve in water. So here we see a protein, an enzyme lysozyme, but water molecules can surround it and form a hydration shell. So you can dissolve this protein in water. It depends on the nature of the protein. If it's a really hydrophobic protein, who knows what hydrophobic means?
It doesn't dissolve in water.
Well, it hates water, right? It doesn't like to interact with water. And so a hydrophobic protein is one that's not going to dissolve in water. But protein can have hydrophilic regions and hydrophobic regions. And we'll see how important that is when we start talking about membranes, because membranes are mostly fat, and fat is a nonpolar hydrocarbon that does not like water. It's hydrophobic as well. So, but a hydration shell can form around molecules that have charges associated with them, whether it's a full ionic charge or just a partial charge. So, as I was just saying, hydrophilic means it loves water. Hydrophobic means it hates water. So a hydrophilic substance has charges associated with it, so it can interact with water molecules, right? Because water molecules are polar. Hydrophobic substances, they don't like water. They're nonpolar. And so it's like mixing oil and water, right? They don't mix. As hard as you try, you can't mix oil and water. You can't make a solution of oil and water unless you include some other compounds, which we're not going to get into, right? But oil is very hydrophobic. It's nonpolar, and so they don't like water. So the layer of oil will form on top of the water, right, to minimize its contact with the water because they don't like each other. A colloid is a stable suspension of fine particles in a liquid, like milk. You know, whole milk has 4% milk fat, but it's homogenized, so the fat is evenly distributed throughout the milk. Real milk, you know, straight from a cow, the fat will separate, and we call that cream, right? And then the liquid watery stuff is underneath. Butter, same idea. We have fat evenly mixed all throughout the butter. A peanut butter, and we're talking about, you know, the store-bought kind, like, I don't know, a Jif or the generic brand you buy at the store, not ground peanuts. If you just use ground peanuts, after it sits, the oil separates, right? It floats on top. And then you got to mix it all back together before you use it. But the stuff that most people buy in the store has certain chemicals added to it, which allows for the fat to be evenly dispersed through the product. And so the fat doesn't separate. So we call that a colloid. Most biochemical reactions occur in water, right? Because cells are full of water and cells are surrounded by water. And the chemical reactions depend on collisions of molecules, and therefore the concentration of solutes in aqueous solution. More solutes floating around means there's more likelihood for them to collide with each other and react to form a product. So molecular mass is the sum of all the masses of the atoms in a molecule. The numbers of molecules are usually measured in moles. So here we're doing some more chemistry stuff. For those of you who've taken chemistry or are taking it, you've talked about moles, so you're very familiar with this. But by definition, 1 mole of atoms or molecules is equal to 6.02 times 10 to the 23. So a big number, right? But atoms and molecules are small. But this is Avogadro's number, right? The scientist that came up with this. And so the unit Dalton is used to talk about molecular weight. So 6.02 times 10 to the 23 Daltons is equal to 1 gram of a substance. So 1 gram contains 6.02 times 10 to the 23 molecules of that substance. So that's the definition. So a Dalton is equivalent to the atomic mass unit, right? The molecular weight, or the grams per moles. Now, if you make a solution and you make it using moles, we call that a molar solution. And the concentration is molarity. Again, the people who have taken or are taking chemistry, you probably have already talked about this. But molarity is the number of moles of solute per liter of solution. So it's relative to the liter. So it's a standard measure of concentration, is molarity. But it's moles per liter. And the liter is typically water. So now, when it comes to the relationship between grams, molecular weight, and moles, this is something you should memorize because this shows you the relationships between grams, molecular weights, and moles. And for those of you who have taken or are taking chemistry, I think some of you said that you have or are taking it. Have you ever seen this before? Has anybody ever seen this grams, molecular weight, and moles, little diagram? No. And chances are you won't see it because whenever I've asked my students, who are taking chemistry, because some students take chemistry along with 150, they say that they were not, told to, look at it this way. They weren't given this, neat little relationship, but it's something that you should remember because it makes all the relationships and how to calculate them very easy to remember. So how do you use this? Well, grams, when divided by molecular weight, equals moles. Right, so grams divided by molecular weight equals moles. Grams divided by moles equals molecular weight. And molecular weight times moles equals grams. So this is all the relationships between grams, molecular weight, and moles in one very easy to remember formula. And this is something that my chemistry professor taught me a very long time ago now. And for some reason, they stopped teaching this, and I don't know why. But grams divided by molecular weight equals moles. Grams divided by moles equals molecular weight. And molecular weight times moles equals grams. So all the relationships that you need to know, right, to calculate either grams, molecular weight, or moles. So in our question, you're going to make a 1 molar solution of calcium chloride, CaCl2. You would place how many grams of calcium chloride into a container and then add how much pure water to that container. So here are the masses of all the atoms involved. So you have the mass, you have the molecular weights. So now you need to calculate how many grams to make 1 mole, and then you're going to add that 1 mole to how much water. So take a couple minutes, play with this, right? So you're being given all the molecular weights for all the atoms. You need to calculate how many grams for 1 mole of calcium chloride, and then how much water would you add, to make 1 liter of a 1 molar solution.
Is molecular mass the same as molecular weight?
Yep. So who thinks they know the answer? So who thinks they know? Right, so you first have to calculate how many grams of calcium chloride is equal to 1 mole. So using our formula here, right, we know we only want 1 mole. And molecular weight times moles equals grams. So molecular weight times 1 will be the number of grams of calcium chloride. So we have 1 atom of calcium has a molecular weight of 40. We have 2 chlorines. A chlorine atom has a molecular weight of 35, so there's 2 of them, so that's 70, plus 40 makes 110. So that's the molecular weight, 110. We only want 1 mole, so 110 times 1 equals 110 grams. So that's how many grams of calcium chloride, right, for 1 mole. So you want to make a liter. Do you just add your 110 grams to 1 liter of water?
No.
No, right? You would think that that's how you would do it, but a liter of water is 1,000 grams of water. And then you're adding 110 grams to that 1,000 grams. Well, that's more than a liter, right? So your concentration is actually going to be lower than 1 molar if you do it that way. So you would add enough water to make it up to 1 liter. And so if you were to go by grams, you could add 900 or 890 grams of water, right? And then together you'd have 1,000 grams of your solution. Or you just put it into a flask, and then fill the flask up to 1 liter. And then you'd have your 1 liter of solution. So we are actually going to learn how to make a lot more solutions in some future labs. And so you will see all this again. And we will also use our concentration formula, which I talked about last time. A times B equals C times D. It's that simple formula, right, to calculate concentration. So it's not complicated. It just looks complicated. But memorize this formula. Know these relationships because it's very easy to remember if you remember that, right? Because that tells you all the relationships between grams, molecular weight, and moles. But for some reason, in most places, they don't teach that. It's easy, right? I like to do things that are easy. So any questions on how we solve this problem? Right, a 1 molar solution means 1 mole per liter. So we had to calculate how many grams was equal to 1 mole. So we added up the molecular weights of calcium and 2 chlorines, and that was 110. And that's the molecular weight. And we wanted 1 mole, so molecular weight times moles, 110 times 1 mole equals our grams, 110 grams. And then we add enough water to bring it up to 1 liter. So when it comes to acids and bases, right, here we're talking about pH. So hydrogen atoms in a hydrogen bond between two water molecules can shift, right, from one molecule to the other. So the hydrogen atom leaves its electron behind and is transferred as a proton or a hydrogen ion, so H+. As I mentioned before, sometimes we just call hydrogen ions protons because that's all they really are. The molecule with the extra proton is now a hydronium ion, H3O+, though for simplicity, we often just say it's H+. And then the molecule that lost the proton is now a hydroxide ion, OH-. So technically the H+ is really H3O+, but we normally write the dissociation of water, H2O, as H+ plus OH- for simplicity, right? In reality, it's H3O plus OH-. And so we would need 2 water molecules to balance that equation. But for simplicity, this is how you should just think about water dissociating into H+ ions and hydroxide ions. So H+ and OH-. And so water jumps back and forth, between a water molecule and its dissociated compounds. As we see here, right? It's technically H3O+, but for simplicity, they say just H+. But if it's H3O+, you have to balance the equation and make it 2 water molecules. It's easier to think of it as just one water molecule dissociating into H+ and OH-. The dissociation of water molecules does have a great effect on living organisms. If you change the concentrations of H+ and OH-, so you're changing the pH, that can have a drastic impact on the chemistry of a cell. So all living organisms exist within a narrow pH range. And that's because if it's too acidic or too basic, also called too alkaline, those cells will die. They won't be able to perform all the biochemical reactions, because it's either too acidic or too basic, and that screws up the chemistry. When it comes to pure water, there are equal concentrations of H+ and OH-. Adding solutes to the water, called acids and bases, will change the concentrations of H+ and OH-. We use the pH scale to determine acidity or alkalinity. So H+, a lot of H+ means it's acidic. A lot of OH- means it's basic or alkaline. An acid is any substance that increases the H+ concentration of a solution. And a base is any substance that reduces the H+ concentration, which means the OH- concentration is going to increase. This didn't convert quite well, so it looks messed up here a bit. When you use brackets around something, brackets mean concentration. So whenever you see brackets around atoms or molecules, it means concentration of that atom or molecule. And so for water, the concentration of H+ and OH- is 10 to the negative 14. And so the definition of pH, and be thankful we're not calculating pHs in this course, a pH is the negative log of the concentration of hydrogen ions. And believe me, there's all kinds of math you can do to calculate pHs, which we're not doing in this course, but if you are a science major and you're majoring in biology, you may take a biochemistry course in which you're going to do a lot of this stuff. So a neutral solution, or neutral aqueous solution, the concentration of H plus is 10 to the negative 7. And so if you plug that into the equation, minus the log of negative 7, it equals 7. So that's how we get the pH scale, the numbers. But you don't have to remember the math here. But it's based on the log of the concentration of H plus. And so a neutral solution, which has equal concentrations of H plus and OH minus, has a pH of 7. A solution that has a pH of less than 7 is acidic. A solution with a pH above 7 is basic or alkaline. Most biological fluids have a pH between 6 and 8. And when it comes to cells, it's much more narrow than that, right? It's 6 to 8 because a pH of 8, oceans, salt water, seawater, has a pH of 8.3. So all the forms of life living in the oceans are living at an alkaline pH, 8.3. The internal cellular environment for our cells is right around pH 7. And you really can't go much above or below. And I mean like, pH 7.3, pH 6.8. It's a very narrow range around pH 7. Otherwise, our cells will die and we will die. There are certain organisms, they live at the extremes. There are organisms called acidophiles, which love an acid environment, and they can grow in pH 2, very, very acidic. And we have other organisms at the extreme that can grow in much higher pHs. But again, they're living at those ranges. They also have a very narrow range, but it just happens to be either very acidic or very basic. Most everything else likes it right around pH 7. So here we see the pH scale. And this is one of those things that sounds kind of like, well, it sounds strange. So a low pH means high acid. A high pH means low acid. So a low number is very acidic. It's high in acidity. pH 1, pH 2, pH 3, very, very acidic. A high number is very basic, it's very alkaline. So things like battery acid, right around pH 1. Your stomach acids, right around pH 2. So your stomach acids are very acidic. So that's kind of a gross example, but some people have eating disorders like bulimia, where they make themselves throw up after they eat. Those people tend to have very bad teeth because all the stomach acid on those teeth will cause them to rot, right? Because it's very acidic, a pH of 2. Lemon juice also has a pH right around 2. So lemon juice is like your stomach acid. So it's okay to add a little bit of lemon juice to water because you're diluting it. But you should never suck on lemons. I know some people like to suck on lemons. Never do that. They're way too acidic. You're really damaging your tooth enamel when you do that. So don't suck on lemons. A little bit of lemon juice in your water or drink is fine. But do not suck on lemons. Oranges are okay because they're nowhere near as acidic as a lemon is. Stay away from lemons. I don't know about limes, but since they're very close to lemons, I would avoid sucking on limes as well. Right? They're way too acidic. You're damaging your tooth enamel if you suck on lemons, so stop doing that. I know some people like to do that. Vinegar, beer, wine, and cola, right around pH 3, so they're actually also very acidic. Wine and cola, they can stain your teeth, right? Because they're doing damage to the enamel. A tomato juice, black coffee also stains your teeth because it's acidic, so it eats into your tooth enamel, which is why people that drink lots of coffee, it turns their teeth kind of a brownish, yellowish color. Rainwater is actually slightly acidic, maybe due to pollutants in the atmosphere. Urine's right around 6, saliva, pure water, blood, tears are right around 7 because our cells need the pH to be right around 7. Seawater, I said, is pH 8.3, and it's full of life, not just big things like the fish, but enormous numbers of bacteria and viruses in seawater. Right, so pH 8.3 is ideal for them. Milk of magnesia is something that's kind of nasty if you have to, take any of it, but it does help to neutralize stomach acid. So sometimes people take milk of magnesia when they have heartburn because it neutralizes the stomach acid. Ammonia above pH 11, so very, very alkaline, very basic. Bleach, oven cleaner. Oven cleaner is actually either sodium hydroxide or potassium hydroxide. It's good for helping to clean your ovens because that very high pH will help to break down proteins and fat. And so that's why it's much more effective than using an acid, right, to clean your oven, like vinegar. And the way that soap was originally made, originally when humans were trying to find, some way to clean themselves, they discovered that mixing lye or sodium hydroxide with animal fat is how you create soap. And as an experiment that you should not do, if you had some oven cleaner or some drain cleaner, because they include the sodium potassium hydroxide as well, right, to digest away the proteins and fats that are clogging your drain. If you were to put some on your hands and rub your hands together back and forth, they would get soapy. And it's because the alkali, right, the hydroxides, are converting the fats and oils on your skin into soap. So that's how they used to make soap, using animal fat. Most soaps today are not made using animal fat, but you can still buy some soaps that are made with lard, or what they call beef tallow, which is animal fat. Any questions on pH? A lot of H plus means it's acidic. Very little H plus and a lot of OH minus means it's very basic or very alkaline. Right, so alkaline and basic means the same thing. So I use those terms interchangeably. You may hear them, but basic and alkaline or alkaline means the same thing. So an acid will donate H plus in a solution, and bases will donate the OH minus or accept the H plus in the solution. If a solution has a pH of 7, it has equal concentrations of H plus and OH minus. If you got more H plus, you have an acidic solution. If you have more OH minus, you have a basic or an alkaline solution. Either extreme is bad for most organisms. Acids and bases are able to, destroy enzymes and other proteins equally well. And that's one of the reasons why cells exists within a very, very narrow pH range. I mean, very narrow. A buffer is a substance that can minimize changes in the concentration of H plus and OH minus. So most buffers consist of an acid-base pair which can reversibly combine with the H plus. So what that means, if excess H plus is being created, the buffer can absorb it and neutralize it and pH back to neutral if we're talking about cells. And if too much base and too much OH gets created, that can also be absorbed. And again, the pH is brought back to around neutral. So I use neutral since we're talking about cells, but you do have different kinds of buffers that can maintain different pHs depending upon what the buffer system is. But we're just talking about cells here. And so we typically use either a bicarbonate buffer or a phosphate buffer inside our cells to maintain the proper pH. So we have to create these buffer solutions, these natural buffer solutions in our cells because some of our cellular processes make H plus. Other cellular processes make OH minus. And so a buffer helps to maintain that constant pH. And so we typically use bicarbonate and phosphate buffers in our cells in order to maintain a neutral pH. So in humans, our blood pH is around 7.4. A decrease in blood pH to 6.4 would be fatal. And so it doesn't sound like a big difference, right? To go from 7.4 to 6.4, but remember I said it's a very, very narrow range of pH. And so one pH unit, different in your blood will kill you. So if your blood pH is 6.4, that's way too acidic and you will die. Even though 6.4 is not really very acidic, at the cellular level, it's very acidic and enough to kill you. And same thing, if your blood pH were to go up to 8.4, you would also die. So a very narrow range. But if your blood pH does drop to 6.4, what does a drop by 1 pH unit represent? I have an E. I have 10 times as many. So each pH unit, 1, 2, 3, all the way up to 12, is a difference of 10, right? Because it's the log of the concentration. So each pH unit differs by 10. And since we know a lower pH number means more acidic, more H plus, and each pH unit is 10 times different, right, than the one before it, that must mean there's 10 times as many H plus ions in the solution. So your pH units change by a factor of 10. So that's why it's so dramatic. And that's why you might think, well, 7.4 to 6.4, that's not a big difference. It's 10 times difference. It's 10 times more H plus. And that's a huge difference. And that's why I said the pH range inside of a cell is actually very, very narrow. It's really narrow. And that's why we need these buffer systems, bicarbonate and phosphate. And so if we have a bicarbonate solution, the equilibrium between those solutions is carbonic acid and bicarbonate. And that's how we regulate pH. So H2CO3 is carbonic acid, and that will dissociate to form the bicarbonate ion and hydrogen ions. And so the reaction can shift either to the left or to the right. in order to maintain the proper pH inside of the cell. And so the question is, as the blood pH begins to rise, what will happen? So in what direction will this chemical reaction proceed? Will it move further to the right and make more bicarbonate ion, an H plus ion, or will it go to the left and make more carbonic acid? If your blood pH increases, what do you think will happen? I have a D. Okay, but if the reaction proceeds to the left, is more carbonic acid being formed? Right, because the acid is H2CO3. If you're going to the left, right, you're making more of that, but is that what you want to do? I'm just asking. I'm not saying if you're wrong or anything. Right, so we're making more OH minus. So we need to neutralize the minus. So what would be a good way to neutralize the minus? Make more H plus. So then what would the answer be? Or what is the correct answer? Right, so your pH is rising, which means more OH minus is being produced. And we need to neutralize the OH minus. And the way we neutralize the minus is with more H plus. And so A is actually the correct answer. Right, the reaction will proceed to the right so that more carbonic acid dissociates to create the H plus, which will neutralize the OH minus. Now, if the question were reversed, what would happen as the blood pH begins to decrease, right, or more H plus was forming, then you'd go to the left, right, to make more carbonic acid, right? So, but this is how buffer systems work, right? They work to help neutralize increases or decreases in the pH in order to maintain that constant pH. And for our cells, that's usually right around pH 7. It doesn't take much above or below pH 7 to cause serious problems. And so that's why we have these buffer systems. But even still, you can overwhelm a buffer system, right, by adding way too much acid or way too much base, and the buffer system can't handle it. And there are conditions where sometimes that happens, due to medical conditions and things. So, but any questions on what we've done? So just as an interesting kind of FYI, when they make distilled or deionized water, which is what we use in the lab, we need that pure water. It turns out that the pure water actually does have a somewhat acidic pH, around pH 5, between 5 and 6. But if it's pure water, it's supposed to have a pH of 7. And what happens is that over time, as water sits exposed to the atmosphere, it can absorb some carbon dioxide, which makes carbonic acid in the water. So if your pure water sits exposed to the air, it can actually become a little bit acidic, and that's due to the carbon dioxide in the air. If you take water and you blow through a straw and you blow into the water, you're blowing a lot of CO2, which will make carbonic acid and lower the pH of water. So that's something that is kind of weird when you think, oh, well, this is pure water. It should have a pH 7, but it actually tends to be around pH 5. It's because the carbon dioxide from the air is dissolving into the water and creating a little bit of carbonic acid. So if you ever have a situation where the pure water is acidic, it's most likely because CO2 dissolved in it and is making some carbonic acid. No, we don't do that actually. Normally by the time you make up whatever you're doing for your solution, but when it comes to the biotechnology and all those kinds of solutions that are made, they typically include buffers in the solution so that you always have the exact pH that you want. But if we make up something like a sucrose solution, no, we don't bother with the pH because it's not a big deal. But it is a weird phenomenon when it's like, well, if it's deionized water, if it's pure water, why is it acidic? It's because if it sits long enough and it's exposed to the atmosphere, CO2 will dissolve in it to make some carbon dioxide. And you can speed it up in our biology 101 labs. When we do photosynthesis in 101, not the same experiments we do in 150, but we have a pH indicator and we blow into tubes of water and we see the pH indicator change color because the water is becoming acidic, right? The CO2 is making carbonic acid. So it's a real thing. And you can make it happen more by blowing in the water. But pure water should be pH 7, but CO2 can cause some carbonic acid to form. So that's just an FYI kind of thing because you don't expect, right, your distilled or deionized water to be acidic, but sometimes it can be, even though it's pure water. It's because of CO2 in the atmosphere. So, any other questions or comments? All right, so we're done with lecture for today.